Welcome students to the next session on transition metals. You learnt that transition metals have incompletely filled d orbitals. This gives rise to certain very characteristic properties to transition metals. You see on the screen the list of the properties which arise out of incompletely filled d orbitals. We will take them up one by one for detailed discussion. The first one is the transition metals have high enthalpies of atomization. What do you mean by enthalpy of atomization? It is the energy or heat required to separate the atoms. Now, in the earlier concept of metallic bond, you might have learnt that metal ions are embedded in a pool of electrons. Greater the number of valence electrons of the metal, more electrons will be in the electron pool and stronger will be the interatomic bonding. Now we will see a graphical representation of enthalpies of atomization of the transition element. As you move along a row of transition metal, you see that the melting point increases. The melting point is plotted on the y-axis, and so as you move from left to right on the x-axis, you see the melting point increases. Actually, as the number of unpaired electron increases, the melting point also would increase, because the atomic orbitals of the unpaired electrons overlap to form stronger interatomic bonding. You also observe that manganese and technetium have a depression in the graph, isn't it? That is because of the stability of the half-filled d orbital. And obviously the last row of transition metals, which is not shown here, that is the 12th group, the elements which are present in group 12, zinc, cadmium and mercury, are very soft and have low melting points because they do not have unpaired electrons and their d orbital is completely filled. In metallurgy, you would again learn that zinc, cadmium metals are refined by evaporation. They are volatile metals and so they can be easily evaporated and purified that way. One more thing that you observe is that the 4D and 5D elements have higher enthalpies of atomization compared to 3D. What could be the reason? Greater enthalpy of atomization means greater availability of valence electrons. These valence electrons come out more readily to form the interatomic bonding, hence they have higher enthalpies of atomization than the 3D elements. So in a nutshell, if you are asked to give a reason for the high enthalpies of atomization of transition metals, you have to state precisely that it is due to the availability of larger number of valence electrons from the ns and n-1 d orbitals. Students, in this session I will be explaining to you how to answer certain questions where you are required to give reason for the given statements based on the properties of transition metals. Read the first question. Transition metals have high density and are less electropositive than alkaline earth metals. Now for explaining the higher density of the transition metals compared to the alkaline earth metals, you have to recall that the transition metals have large number of valence electrons, in considering the electrons in the ns and n-1 d orbitals. Due to larger number of valence electrons, the interatomic attraction in transition metals is high. This we already saw in connection with the high enthalpies of atomization of transition metals. Due to the greater interatomic attraction, the volume of the transition metal for the given mass of the metal is less compared to that of the alkaline earth metal. So the density is higher. For density, we have to see mass by volume. Since the volume is less, transition metals have higher density than the alkaline earth metals. Now coming to the second part of the question, you have to explain why transition metals are less electropositive than alkaline earth metals. To explain the electropositive character, you have to consider the ionization enthalpy of the transition metals. And what determines the ionization enthalpy? It is the charge by size ratio. You already know that the transition metals are having lesser atomic size due to higher nuclear charge and poorer screening by the d electrons. Hence, the size is less compared to compared to that of the alkaline earth metal. So, charge by size ratio is high, due to which they are less electropositive than the alkaline earth metals. You are required to write the answer in the following way, which I will be giving you now. Let us pass on to the second question. The second question goes like this. CuCl is colorless while CuCl2 is blue. Why? The color of the transition metal is to be associated with incompletely filled d orbital. In CuCl, copper is monopositive and the monopositive copper has the configuration 4s0 3d10. While the dipositive copper in CuCl2 has the configuration 4s0 3d9. So, it is obvious that the Cu2 plus has an incompletely filled d orbital and hence it is colored, while in CuCl, due to completely filled d orbital, it is colorless. You can write down the answer as I am going to give you now. Now read the third question. Pt4 is more stable than Ni4 while Ni2 is more stable than Pt2. Here I would like to tell you that to explain the stability of an ion, you should remember that it should have less ionization enthalpy. Nickel, palladium, platinum lie in the same group, that is group 10. If you take up the sum of the first 4 ionization enthalpies of platinum, it is less than that of nickel. But the sum of the first 2 ionization enthalpies of nickel is less than that of platinum. So that explains the reason. Now for the same reason, the question can be asked in a different way. Note it, K2PtCl6 is known while corresponding compound of nickel is not known. It's not known. What is the oxidation state of K2PtCl6? It is +4. We just now saw that the +4 state for platinum is more stable than that of nickel. So, a corresponding compound of nickel does not exist. The answer is the same for both the questions. The fourth question goes like this. Hydrated copper sulfate is blue in color while anhydrous copper sulfate is colorless. You know, hydrated copper sulfate should be written as CuSO4.5H2O. In fact, it exists as CuH2O 5 times SO4. This is said to be a coordination compound. That is a subsequent unit on coordination compounds, in which you will be learning about coordination compounds in great detail. Now these water ligands split the d orbitals of the copper ion into 2 sets of T2g and Eg orbitals. T2g and Eg orbitals having difference in energy, and electrons can be excited from the lower level to the higher level by absorbing energy from the visible region. That is the reason why copper sulfate pentahydrate is colored. In the case of the anhydrous copper sulfate, the d orbitals of the copper ion or degenerate or of the same energy. I suppose you have understood the reason. Now you can write it in words. I suppose you have gone through the answer and understood that. Let us pass on to the fifth question. MnO4 2 minus undergoes disproportionation. What is a disproportionation reaction? It is one in which an ion undergoes simultaneous oxidation and reduction. MnO4 2 minus ion or manganate ion undergoes disproportionation in the following way. 3 MnO4 2 minus plus 4H plus giving 2 MnO4 minus plus MnO2 plus 2H2O. At this juncture, I would like to tell you that it is important for you to remember this equation. You could be asked to give an example for the disproportionation reaction of manganese in particular or any metal in general. So better learn this equation. In MnO4 2 minus, Mn exists in plus 6 oxidation state. Remember, atom has a configuration of 4s2 3d5. So for plus 6 state, it will be left with just one electron in the d level. It will have d1 configuration. I would write it like this. MnO4 2 minus has d1 configuration. You know this is highly unstable. MnO4 minus will have d0 configuration, which is stable, and MnO2, which has plus 4 oxidation state, will be left with d3 configuration. Here oxidation state is plus 6, here oxidation state is plus 7, and here oxidation state is plus 4. So the unstable D1 configuration can pass on to the stable D0 and D3 configuration. This explains why MnO4 2 minus undergoes disproportionation. Having written the answer, let us pass on to the sixth question. Transition metals exhibit their highest oxidation states in fluorides and oxides. When we say fluorides and oxides together, what comes to your mind? It's their high electronegativity and small size, isn't it? That is actually the reason. The fluorine and oxygen atoms with their small size and high electronegativities are able to excite the transition metal atoms to their highest oxidation state by providing necessary energy. Let us write it down. I suppose you are able to read it clearly. The fluorine and oxygen atoms with their small size and high electronegativity are able to excite the transition metal atoms to their highest oxidation states by providing the required energy. In the seventh question, let us give reason for the statement why Mn3 plus is a good oxidizing agent and Cr2 plus is a good reducing agent. Mn3 plus, when it is acting as an oxidizing agent, will get reduced to Mn2 plus. For such questions, you have to compare the stability of the two oxidation states, Mn3 plus and Mn2 plus. What are their configurations? In Mn2 plus, Mn has 5 electrons, 5 electrons in the d level or d5 configuration. That is a half-filled level of d orbitals. You know that is very stable. Hence, Mn3 plus will have a tendency to readily pass on to Mn2 plus state, thus acting as a good oxidizing agent. The reverse is true for Cr2 plus. Cr2 plus, while acting as a good reducing agent, will be oxidized to Cr3 plus. Cr3 plus will have 3 electrons in the d level, which will be half filled T2g level of d orbitals, which is again a stable state. Students, I would tell you that it is very important for you to know the electronic configurations of the transition metals in different of oxidation states. Only then you will be able to answer such questions. So let us write down the answer now. An ion would have a tendency to pass on to a state with more stable electronic configuration. It will achieve this by acting as a good oxidizing agent or a reducing agent. The eighth question reads thus: manganate ion is paramagnetic while permanganate ion is diamagnetic. Manganate ion is MnO4 2 minus. In it, Mn is present in the +6 oxidation state with a configuration of D1, just one electron in the D level. You know, paramagnetism arises due to the presence of unpaired electron. Hence, it is paramagnetic. Now take a permanganate ion with MnO4 minus Mn in +7 oxidation state with no electron in the D level, D0 configuration. Obviously, it is diamagnetic. It's a very simple question. The last question of this session is: scandium does not form monoxide or it does not exhibit +2 oxidation state. Explain why. You know, the common oxidation state of the first row transition metals is +2. But scandium, having an electronic configuration of 4s2 3d1, cannot exhibit +2 state. If it exhibits +2 state, it will be left with just one electron in the D level with D1 configuration, which is highly unstable, you know. Hence, it does not exhibit +2 state, or it does not form an oxide of the formula SCO. Let us write the answer. I suppose the session was useful to you. I'll continue to discuss some more questions in the next session. The second property of transition metals to be taken up for discussion is variable oxidation states. Transition metals exhibit a large number of oxidation states. The oxidation states exhibited by the first row transition metals is given in the table on the screen. You know that the transition metals have their valence electrons in ns and n-1 d orbitals. The energy difference between these two orbitals is quite less. So, the electrons from both these levels can be used for bond formation. That is the reason why they exhibit a large number of oxidation states. When the metal loses its electrons only from the ns level, or when it uses only the ns electrons for bond formation, it exhibits an oxidation state of +2. In fact, +2 is the common oxidation state for all the transition metals. But you see that scandium exhibits only +3 and not +2. Can you think of a reason? It's not difficult for you to guess that scandium has a configuration of 4s2 3d1. When it loses its two s electrons, it will be left with just one electron in the d level, which is not a very stable condition. Hence, it loses all the 3 electrons for bond formation. Similarly, titanium exhibits +4 as the common oxidation state, in which case it loses its 2 ns electrons, 2 4s electrons and 2 3d electrons. For chromium, you see that +3 and +6 are given in bold letters. That means these are the 2 common oxidation states. How does it exhibit +3? See, chromium has a configuration, electronic configuration of, just a minute, chromium has an electronic configuration of 4s1 3d5. Now, when it loses 3 electrons, Cr3+, it will have a D3 configuration. Now then, d orbitals, 5 d orbitals, though we say they are degenerate, they are actually split into two sets of T2G orbitals, and EG orbitals. T2G orbitals have 3 d orbitals, 3 numbers of d orbitals, and EG set has 2 numbers of d orbitals. EG orbitals are at a slightly higher energy level than T2G. Now, when 3 electrons are present in the d level, those are present in the T2G level, that is with 1 electron in each, that will be a half-filled d orbital set, hence that would be a stable condition. And for plus 6 it loses all its s and d electrons, 4s electrons and 3d electrons. For Mn, the two oxidation states are plus 2 and plus 7, which are given in bold letters. The plus 2 state arises when Mn loses its 4s electrons. See, in MnCl2, MnSO4, in these salts, it is exhibiting an oxidation state of plus 2. And in KMnO4, manganese is exhibiting an oxidation state of plus 7. There are a few facts that you should know with regard to the oxidation states of transition metals. A transition metal exhibits a maximum oxidation state of plus 8, which is shown by osmium in OSO4. And the lowest oxidation state exhibited by a transition metal is 0, which is exhibited by nickel in nickel carbonyl, NaCO4. Then one more thing is, in the lowest oxidation state, the metal exhibits ionic character, it will be exhibiting ionic character, and the highest oxidation state, it will be exhibiting a covalent character. That is, Mn, again we will take, for example, Mn2 plus, I say, would be ionic, and Mn plus 7 state would be covalent. You know MnCl2, MnSO4, the salts which are commonly given for salt analysis in the laboratory. These salts are soluble in water and respond to tests when you add the reagents. This will be possible only in ionic reactions. That means Mn2 plus is present as ions in these salts. That proves the ionic character of Mn2 plus state. In Mn plus 7, that is in KMnO4, manganese is covalently bonded to the 4 oxygen atoms. So here it exhibits a covalent character. One more thing you should know is, the lowest oxidation state of a transition metal is basic. Mn plus 2 again is basic in nature. What do we mean by that? When MnO, let us take the oxide of manganese, MnO, dissolves in water, it forms manganese hydroxide, which is a base. Mn2O7, in which manganese exhibits an oxidation state of plus 7, this is the lowest and this is the highest. It dissolves in water to form HMnO4. This is permanganic acid. Potassium permanganate is a salt of this acid. This is acidic. So this proves that, establishes the fact that in the lowest oxidation state, a transition metal, here it is Mn plus 2, shows basic nature, and in the highest oxidation state, the metal shows acidic character. This is only a statement of fact. What is the reason for that? Mn2 plus ion is large and its nuclear charge is small. So it still has d electrons to give. So it would be acting as basic. You know, according to Lewis concept, a substance, something that can give away electrons exhibits basic character, and something that accepts electron exhibits acidic character. I said Mn2 plus is having less nuclear charge and it has more electrons to give away, so it behaves as a base. Mn plus 7 on the other hand is very small and its nuclear charge is high. It will have a tendency to borrow or gain electrons, hence it exhibits acidic character. So here I have given answer to a reasoning question that a metal in its lowest oxidation state is basic and in its highest oxidation state is acidic. I suppose it is clear to you. This is with regard to variable oxidation states of transition metals. The third property is that transition metals form colored ions. If I ask you to name a few colored salts in the laboratory, you may be coming up with potassium chromate, which is yellow in color, dichromate, the orange crystals, potassium permanganate, the deep purple crystals, and then copper salts, nickel salts, and manganese salts, which are buff colored. Isn't it so? So these are all colored salts which you come across. In all these salts you will find transition metals. So we can say transition metals form colored ions. Now we have to give reason for that. You know that transition metals have incompletely filled d orbitals, or they have unpaired electrons in the d orbitals, incompletely filled d orbitals, or we can also say that as they have unpaired electrons in d orbitals. Now these d electrons can undergo dd transition. What is this dd transition? Just a while ago I told you that the d orbitals are split into two sets of 3 orbitals and 2 orbitals called T2g and Eg, with a slight difference in their energies. The electrons, unpaired electrons in these d orbitals, can gain a small amount of energy from the visible region and then get excited to the higher set of d orbitals, which we call dd transition. So they exhibit very strong colors. I suppose you will be able to state the reason clearly for the transition metals forming colored ions. You have to say these three facts. Incompletely filled d orbitals. They have incompletely filled d orbitals or unpaired electrons in d orbitals, due to which they undergo dd transition. So when you say dd transition, we know that it involves energy which they absorb from the visible region. The fourth property is paramagnetic behavior. Now, when substances are attracted by applied magnetic field, they are said to be paramagnetic. When these are repelled by magnetic field, applied magnetic field, they are said to be diamagnetic. Ferromagnetism is an extreme case of paramagnetism. Paramagnetism is always associated with unpaired electrons. Unpaired electrons give rise to two kinds of magnetic field due to its motion. One is due to its orbital motion. The other one is due to its spin. An unpaired electron, due to these two types of motion, creates magnetic field. When we consider the magnetic moment of the electron due to its spin alone, we call it spin only magnetic moment. Spin only magnetic moment, which is given by the formula root of n into n plus 2 Bohr magneton. Bohr magneton is the unit for that, and n is the number of unpaired electrons. That's all it is, very simple. Once you know the electronic configuration of any ion, you will be able to calculate the spin only magnetic moment of the ion. As an example, we will calculate for Mn2 plus. You know Mn2 plus has a configuration of 3d5 with 5 unpaired electrons, 1 electron in each of the d orbital. And so its magnetic moment would be, magnetic moment, spin only magnetic moment of Mn2 plus would be root of 5 into 5 plus 2, that is 7 Bohr magneton, that will be root of 35, which we can say is 5.9 something Bohr magneton. 6 is root of 36, so this is only 35, it should be 5.9 something. I am not taking the exact calculated value, so it is 5.9 something Bohr magneton. So greater the number of unpaired electrons, greater will be the paramagnetic character behavior of the ion. Transition metals and their compounds often act as good catalysts. You have a large number of examples. Nickel, palladium or platinum can catalyze hydrogenation of alkenes and alkynes. Vanadium pentoxide acts as a catalyst in the contact process of manufacture of sulfuric acid. And you can also quote that finely divided iron is the catalyst in the Haber's process of manufacture of ammonium. You can have a very large number of examples for this. Now, we will attribute this to the capability of transition metals to adopt multiple oxidation states. Multiple oxidation states and to form complexes. You know that catalytic reactions are of two types, heterogeneous and homogeneous. In heterogeneous catalysis, I'll come to that. In heterogeneous catalysis, often solids act as catalysts. In the hydrogenation of alkenes and alkynes, when nickel surface is present, the reacting molecules get adsorbed on the surface of the catalyst. So they come in proximity to react and proper collision takes place between the reactants. Also, during adsorption, energy is released which acts as part of the activation energy needed for the reaction. For homogeneous catalysis, we can have the example of the reaction between I- iodide ion and persulfate ion, which is catalyzed by Fe3+. Here we would say that Fe3+ oxidizes I- to I2. So it is going from Fe3+ to Fe2+, and Fe2+ is in turn oxidized by the persulfate ion. So Fe3+ passes on to the other oxidation state, and then this way it provides an alternative route to the reaction having lower activation energy. So when the transition metal passes from one oxidation state to another during a reaction, it takes the reaction actually by a different path having lower activation energy. In certain reactions, it can also form complexes. By doing so also, they lower the activation energy. In the contact process of sulfuric acid, V2O5 acts as catalyst. During the reaction, V2O5 passes on from +5 state to +4 state. So, we would give the reason for the catalytic behavior of transition metals and their compounds as their capability of adopting multiple oxidation states and to form complexes. Transition metals form a large number of complexes. I will give you a few examples. CuNH3 4 times 2 plus, FeCN6 3 minus, FeCN6 4 minus. These are some of the examples which we often come across. In these complexes you find transition metals. You may be knowing that a complex is one in which the central metal ion, that is the copper here, iron here, which are surrounded by large number of negatively charged ions like Cn minus or neutral molecules like NH3, which donate electron pairs that are accommodated in the vacant d orbitals of the metal ions. For a complex formation, two things are essential: charge by size ratio, that is charge by size of the metallic ion ratio. If it is high, will favor complex formation. Also, the metal ion must have vacant d orbitals where the electron pairs that are donated by the ligands can be accommodated. Both these conditions are fulfilled in the case of transition metals. You know, the transition metal ions become smaller as we go from left to right. So the small size of the ions makes the charge by size ratio larger, and they also have vacant d orbitals in which the electron pairs can be accommodated. Hence, transition metals form a large number of complexes. The last one in the list is that transition metals form alloys readily and also form interstitial compounds. No, alloys are solid solutions, you know. Transition metal alloys are of nearly the same size, so one metal ion can easily replace the other in the metal lattice. That is the reason why they can mix in all proportions and form alloys. Interstitial compounds are those in which small small atoms like hydrogen, carbon, nitrogen are trapped in the interstices of the metals, in the lattice of the metal. These atoms are trapped in the lattice of metals like iron. When carbon is trapped in the metal lattice of iron, we have steel. The presence of these metals in the interstices actually reduces the malleability and ductility of the metal, but increases the tensile strength of the metal. You know, steel is much stronger than iron. That is because of the presence of carbon in the interstices, which increases the hardness of the metal. It will retain a electrical and thermal conducting property also, but it will be less malleable and ductile. So this is about formation of interstitial compounds by transition metals.